There is a message. Just be there.
Very good afternoon, friends. I hope I'm audible. So, welcome here for our asset colloquium. And today is a pleasure to have one of our own scientific officer here to give us a very interesting talk on triggering the new discoveries, as you can see. So, let me introduce the speaker. Today we have Dr. Jashal here. He works in our Department of High Energy Physics, Department of High Energy Physics, DHEP, as a scientific officer. And is a senior position, and his major work contribution is towards maintaining and administrating and, of course, doing the research on the computer center, which is set in collaboration with CERN, our hydrogen collider, and, of course, the local as computing power or computational structures or whatever we have here. And now I invite Brij to speak on the research.
Thank you. Thank you very much for the nice introduction, and good evening, everyone. Thank you for coming. And in general, thanks a lot for organizing the asset and all the work related to that. I think we are all set. We can start. As you perhaps noticed, the title of my asset curriculum is Triggering New Discoveries, Advancements in Real-Time Analysis for Expanding Physics Reach at LHCb. And okay. All right. So what I intend to cover today is I want to give you a brief introduction of the LHCb experiment. I will try to introduce to you the paradigm of real-time analysis at LHCb and focus on some of my work in the development of advanced algorithms for high-level trigger 1 at LHCb and its physics impact. Just to give you an epilogue at the beginning itself rather than the end, what I'm going to cover here is most of this talk is based on part of my PhD thesis work. And if you are interested, you can check it out here in the link, the full. This is a significant contribution to the physics program of a major international high-energy physics experiment, wherein it focused on development of the trigger systems and algorithms for the run 3 and onwards, which led to the development of the first full GPU-based trigger system. In addition, the LHCb experiment is now, as effect of this work, is capable of probing lifetime frontiers beyond 100 picoseconds. Earlier, in the run 1 and run 2, LHCb could probe up to 100 picoseconds, but now you can probe up from 100 to 2000 picoseconds. And this is a huge impetus to the physics program with standard model and beyond standard model physics. And I would try to explain the work which has gone behind it. But just to take a bit of a step back, one of the cornerstones of our understanding of this physical world is the standard model of the particle physics, which provides the framework for understanding the behavior of the fundamental particles and their interactions through strong electromagnetic and weak forces. And standard model's predictive capabilities are a testament to its success, as you can see on the right, where you can see that experimental measurements closely match with the predictions of the theory. But however remarkable it is, there are still many unanswered questions such as why there are these three generations of fermions and why there's so much difference in the masses. Also, we know that at the beginning of the time, there was an equal amount of matter and antimatter. But now in our universe, there's hardly any antimatter. In addition, we need to understand other probable constituents of our universe, such as dark matter and dark energy. So moving on, one of the areas, one of the promising avenues for where we can look for these answers and which can help us finding the answers are the study of the long-lived particles. They are there in the standard model as well as beyond. And this is the distribution of the proper lifetime versus the particle mass. As you can see here, you have the promptly decaying W and Z boson from 2 into 10 to the power 20 minus 25 seconds to the stable ones here, which has lifetimes which are protons and electrons which are stable. From the standard model point of view, when I say long particles, what we are interested here in this particular range, where you can see these are the particles which decays in most of our current detectors. For example, lambdas and Kishors and K-longs. So now, just to introduce to you this concept of the lifetime, we know that the lifetime of a particle is the inverse of the decay width, as you can see in this particular expression. And decay width is expressed in this form where we have the coupling constants squared and the mass of the particle. So, for example, for weak decays, the decays involving the weak forces, you will have the coupling constant, which would be lower, and therefore the decay would be lower, and then the lifetime, the tau, would be higher. So perhaps this is more better, yeah. So now looking at some of these. It's not just in the standard model, but also there are many theories in the beyond standard model physics. And if we take a look at some of the leading theories in the BSM models, we can see you have this hidden sector where there can be two scalars which can decay into two long-lived. There can be a particle which can decay into two long-lived scalars. Then you have heavy neutral leptons, where long-lived particle can mix with the standard model and then decay into the final standard model particles. You have SUSI, where there can be existence of these long-lived particles. And then the axion like particles, which are light and neutral, and there can be a pseudo-scalar boson predicted by several extensions of the standard model, and which interact primarily with the two photons here. So there are many models, and there is a lot of interest in this particular area. And here are some of the recent publications where, for example, this one is by overall LLP community, which involves experimentalists and physicists, and the one which focuses on the LHCb specific long-lived particle searches and studies, and one particularly which studies the effect of the high-level trigger on the LLPs. So I would here in these my contribution has been mainly focused on reconstruction strategies and algorithms at high-level trigger to detect these long-lived particles. Now, to introduce the experimental setup, as you know, we have the Large Hadron Collider at CERN, where you collide proton bunches. You have the four major experiments, CMS, where TIFR is part of it. But particularly here in this talk, I'm going to focus mainly on this LHCb experiment. So in a typical proton-proton collision, you have bunches of proton which you collide, and at beam energies up to 70 eV, 6.8 for now, and at the crossing rate of 40 megahertz, and that produces huge data, which then you build around your detector at the collision point. So, for example, this is the LHCb detector, which is a special experiment designed to study heavy flavor decays involving specifically bottom quarks. So this is the BB quark production mainly occurs through gluon fusion, and in the forward and the backward direction. So LHCb is a single-armed forward spectrometer covering about 4% of the solid angle, and can cover about 27% of the B hadron produced in total. And for run 1 and run 3, the detector operated at this luminosity and accumulating about 9 femto-1 inverse of data. Now, with that particular data, LHCb produced some remarkable results. As you can see, to highlight some of these, we have in spectroscopy, it's not just the Higgs boson which was discovered at the LHC, but there were 72 other new hadrons which were also discussed, and out of that 69 were at LHCb. And you would see there are many possible states such as weakly decaying tetraquarks, pentaquarks, and other exotic states which are likely to be waiting to be discovered in the next phase of the LHC perhaps. Then you have flavor oscillations or mixing in the neutral mesons. Here we have the beautiful BS bar mixing, and then you have the world leading measurements of the BS mu mu, and which is a very, very rare process. So just to give you an highlight of what we managed to achieve in the run 1. But now this is run 1 and run 2, and now this is the detector for run 3 of the LHC, and LHCb has carried out major upgrades wherein we have replaced almost all of our detector, more than 90% of the active detector channels with the readout electronics, data acquisition, and trigger system completely overhauled, and it is going to operate at much higher instantaneous luminosity, and about 5 times the instantaneous luminosity. And this is in this run, you can see this is the distribution of the bandwidth at the at which a software trigger has to process the data, the distribution versus the year. And if you look at the LHCb run 3, you have somewhere around 4 terabytes per second, so 40 terabits per second. At that rate, if you basically just record all of its data, you have about 100 petabytes per day, which you are going to get. Obviously, that's a lot of data, and we cannot store it. For example, we have our CMS computing data center with hundreds of servers, about 118, and that has a storage about 13 petabytes. So it's just impossible to basically store all of this data. In the run, and it's not just that, in run 1 and run 2, for example, this was our trigger system. So this is why you need trigger system. You need a mechanism to be able to filter out some of the interesting events and reject some of this. So there was this 3-stage trigger system in the run 1 and run 2, where you had a hardware trigger and then the software trigger. And at such high luminosities, if we see, as you increase in the luminosity, the hardware trigger particularly cannot cope up with the event rate, and it starts rejecting random events, and you can see the relative trigger yields basically plateaus. And so you need, and in order to be able to make these informed decisions, you need to be able to study properties of events in real time. So what do we do in the run 3? Well, if we are as kind as Thanos, we would not discriminate between events, and we just randomly can kill half of them, but we are not. So we need to be able to study them in real time and reconstruct and have an informed decision on what we want to keep and what we not. So that's when it comes to the real time analysis, that you have to make some decisions in the real time when the data is being done, and that's the point. Now, apart from making a decision whether to keep an event or not, you have another level of decision which you can do. If you analyze at a real time, you can choose whether you want to keep the full raw event, which is quite a big size, but you don't have to. You can reduce even, you can have some reconstructed object such as this one and not keep the entire object, not keep the entire raw bank, but keep some reconstructed object that reduces the size of the event. And then you are able to store more. Yes, please. No, this is the trigger system is for general. Yeah. I'm going to come back to why exactly I emphasized in the beginning of the long-lived particle. This is for in general. Yeah. So then if you see the physics program with the RTA model, if you basically if you just only keep the reconstructed objects, you can do much more physics in a limited trigger bandwidth. So our output, the bandwidth is limited, and so you can either play with the average event size by just keeping the reconstructed object, and then that's how you are able to increase your physics. So this basically requires you to reconstruct and analyze the events and select them in the real time. Well, now if I remember in the beginning at 2018 when we started working that, the software trigger at the LHCb was basically running somewhere around 68, processing about 68 events per second, 68 hertz. And if you basically calculate, now if you want to process at 30 megahertz at the software level, you would have needed about more than 4 lakh such nodes. This was on a single node, you would have needed 4 lakh. That would have basically more than 80 million Swiss francs, and that basically goes beyond the budget of the LHCb. So you basically cannot afford that at that particular level of the software. So, but at the end, by 2022, we managed, before the start of the run 2, we really managed to have our software working on different architectures at much higher rate, where we could basically manage it. So I'm going to try to show you how we managed to basically do that. First thing was that, okay, you know that, okay, hardware trigger automatically starts, is not efficient, it randomly starts rejecting. So this was basically, thrown out. What we have is a new trigger strategy where we have the full software trigger. We read at the line rate at 40 terabits per second. And then we process it in 2 stages. One is the high level trigger 1 and high level trigger 2. So as you can see at 100, like for example, at 200 kilohertz, you are able to process the whole thing on about 500 GPU nodes, like two GPUs per node, something like that. Then becomes manageable. But it's not just the GPU. So just going into the details of how exactly this is implemented in a system. You have the LHC bunch crossing rate. And this is where is our high level trigger 1, where we read the full detector and we do the partial reconstruction of the charged particle trajectories and few simple selection lines here. And there we reduce the data rate by about 20 to 40, by a factor of 20 to 40. Then you have a buffer in between where you store this data only for minutes. And at the same time, in the real time, you are processing at the high level trigger 2, where you are supposed to reduce the data rates by a factor of 400. And this reduction must be without the loss of fidelity. You want to keep as much information, as wide information as possible. Going further details here, how exactly this is implemented is you have these different channels which are coming directly from the detector. These are half duplex over 11,000 links, which are coming to this event builder network. And that's where in those particular nodes itself, it's a 4U node where we managed to have 2 GPU cards inserted and managed to save really a lot of money. So about 170 servers in DAC with the event builder, event filtering, you can, with 370, you could possibly do that. But that needed a software to run. It's not the hardware. It's the software which has to run. And that required this particular development. So now coming to the software framework for that. So before I come to the software framework, what exactly do we need to do in this particular software? So mainly our trigger is depending on the track reconstruction. So you basically create the primary vertices and the trajectories of these tracks. Based on that, you are able to make certain decisions. So the problem is track reconstruction. What exactly is track reconstruction? Tracking deals, as you can read, deals with converting the signal from a subdetectors like hits and clusters into a trajectory. And roughly speaking, about 2 phases. One is the pattern recognition and then the track fitting. And why exactly? We need to be able to reconstruct trajectories of the particle in our detector to build vertices, measure decay topologies, and measure momenta, measure invariant mass angular variables, and so on and so forth. And this can be done in different forms of parallelism. Here we have in our framework, in this particular sort of frame, we have 3 levels of framework. You have intra-event, within an event, they can be parallel, you can do parallel things, and then you can process multiple events at the same time, and then multiple bunches of events at the same time. So for this, we built this particular framework. It's called Allen Software Project. And this is a first fully GPU HLT1 framework for any experiment. It's a standalone project and primarily developed using CUDA to process events in the parallel. So you can see different languages which is being used, CUDA, C, C++, and other things. And at any framework, there are multiple layers of software which basically goes into, which has to work together to be fast enough. And so as you can, there are base algorithms, but then there are base libraries, and then on the top you build your compiler infrastructure, performance portability layer, where you can basically run on multiple architectures and so on. At the end, we had a framework which was working, which was supporting multiple architectures, as you can see from different vendors, different types of GPUs, and as well as the CPUs. And so I presented this first, the progress of this in 2019, and then at the end, this was the paper which we published, which is the Allen high-level trigger on the GPUs for the LHCb. Now, coming specifically to the long-lived particles and the tracking, before further going to the algorithms. So we have, as in the beginning I said, we have particles with displaced vertices called LLPs, and distance between the primary and secondary vertex can be about 3 meters if you use this base formula. For example, in the Kishor lambdas and cascades with a typical boost over 10 to 100, you can have it between 3 centimeters to 3 meters. So in the beginning, in the run 1, during the run 1 and run 2, there was no reconstruction of these type of decays, which doesn't leave any signature in the primary vertex locator. This is our velo. And so only because all our tracking was basically, okay, you start looking signatures from the beginning and then you go outside. So as you can see, for example, lambdas and Kishor, their lifetime versus mean flight distances, they come somewhere here. So there were very low poor efficiencies for these standard model. And if you look at some of the BSM physics models, depending upon where they might be, if they have larger lifetimes, efficiencies were basically would plummet to 0. So there was no possibility. For now, just focusing on the LLPs, you have the lambda B to lambda gamma decay. In fact, this is how I actually got into this. In the beginning, my thesis was about studying, performing the branching ratio measurement and angular polarization for this photon in this lambda B to lambda gamma decay. And as you can see, this lambda B goes to final states proton and pion between this lambda, and this is basically has quite high C tau. And if you see the based on where the lambda end vertex is, the number of events, they are much more higher as compared to just being in the velo. So only about 12% were of long events for the in the case of lambdas, and in this case Kishor, so mu about 46%. So our efficiencies for HLT1 trigger on signal in the run 1 and run 2 were less than 10%, less than 25%. And this was basically, okay, why we have these low efficiencies? And so then we started basically exploring why exactly, because most of them were basically downstream the detector, and there we did not have any reconstruction algorithm. Now coming to the algorithms itself, the tracking algorithms, you have, this is another screenshot of the LHCb. As you can see, this is a tracking system. You have the vertex locator where you have the velo tracks, which is very near to the interaction point. At some distance, you have the UT, it's upstream tracker, it's a silicon strip detector, and then you have this new silicon fiber tracker. In between, there's a magnet. So you have these different track types. If this is only, if a track which leaves signature only in the center, it's a velo, and then if some a track traverses all of the detector, that's the long track, and this was our main physics track in the run 1 and run 2. And this is the downstream track, which doesn't leave any signature in the Velo, but only in the last two trackers. So,
sorry,
yeah.
Sorry, I missed. What is Velo stands for?
It's a vertex locator. It's a silicon pixel detector, which is basically specialized for localizing the vertexes of the decays at the very near to the interaction point.
Oh, it's a what kind of detector you said?
It's a vertex silicon pixel detector.
Okay. Thank you.
And so in the run 1 and run 2, the configuration of the HLT, the high level software trigger, was also had very limited number of algorithms. As you can see, there were these different types of tracks and not particularly focused on any of these long-lived decays and tracking. So then this is the current high level trigger one using the LN framework, and you can see the different, so you have the raw data and then the different types of algorithms which are running. So you have the Velo, you have the UT, and then this particular block, which didn't existed in the previous generation of the detector, is now there, where you basically have the these algorithms which are creating tracks on the scintillating fiber detectors and then downstream tracking. So this is where my main contribution has been. Based on these reconstruction algorithms, you have different selection lines, inclusive as well as exclusive, based on the interest of your decay. Then you can write them, and then you can basically have the selection. You select the events, and then you basically pass on to the next stage. Now coming to the first, yeah. Okay.
So sorry, just very where exactly are the long-lived particles decay? Which point?
So, I mean, in this particular sense, the long-lived can be, which is basically not leaving any signature in the primary vertex. So it's after the primary tracker, the Velo. If decays outside this, then this is basically, you can, in this particular detector physics context, you can say that these are the long-lived. Yeah.
Certain band of lifetime,
Brij, can you
cover this in more detail? You would see it. I think it will become clear to you, because here, for example, up until this point, if it's only less than 100 picoseconds, and if it has a lifetime higher, then it can be between 100 to 2000 picoseconds. Yeah.
Brij, can you ask people to use mics when they're asking questions?
Okay. Sure. Thanks. So yeah, now this is our configuration of the new trigger system, and these are the new algorithms which have been introduced. I'll quickly introduce some of these algorithms. For example, in the last tracker, we have the scintillating fiber METs. There are 2.7 meter long fibers with 12 layers of total fibers organized into the XUV configuration. Which is spread over 3 stations of over 1.8 meters. And the UV layers are being tilted by 5 degrees, so that you can basically not just X, but you can also calculate the Y, and to be able to locate the hit. This particular algorithm we did in 2 iterations. In seeding, in first you do in the XZ coordinate system, and then you add these UV information to confirm the Y. And with this formed the basic seed of which you can basically then use to match with other tracking stations to create the tracks. So once you have these seeds, then, for example, you could also match this to the first trackers, which is the Velo, and then you can create a long track. And this was one alternate way of creating long tracks, and this was also quite beneficial, because it's better this way to cover at different momentum ranges, which the forward tracking cannot. So yeah, so I mean, in between, perhaps I wasn't clear about it. Let me, as you pointed out, just make it clear. So you have this magnetic field, dipole magnet, So, you know, when a charge track is passing by here, it has a certain kink here. It basically traverses like this or like this, and that allows us to have the initial momentum estimation of any charge particle. So, so that's why you would see in these this particular curve in the trajectory of the particle.
So just to ask that question, what you are saying in this slide, when you do this sci-fi seed and velo track and you match them, then you compare with, let's say you do that tracking and you get some number of track this match way. But then if I want to see the vitality, whether it is worked correctly or not. So let's say if you have long track reconstructed in standard way, right?
Yeah.
Not in this. Have you compared like the chi-square or whatever of this method with the
Yes.
chi-square and
In fact, I mean, the current tracking, current HLT1 configuration, we are going to use both the forward as well as the as well as the matched long tracks, because we have seen that for certain low momentum ranges, the matching performs better than the forward. And in terms of the performance also, you have seen these differences. So they are in certain areas of the momentum ranges, they are complementary to each other. So that's why the trigger configuration is now such that you use both the tracks. Based on both the type of track, you write a selection line and then you make a decision whether to keep it or not. So then this as a seed algorithm, you can see it performs quite well with quite good efficiency, more than 80%, with very good momentum resolution for the matching and very low ghost rates as well. And for more details, we had documented this algorithm in this particular paper. Now coming to the downstream track, just to remind you again. So you have the T tracks, which are the fiber scintillating fiber tracking stations. I just now showed you that okay, we can create these seeds from these. You have the option of basically matching this to velo, but if you just match them, filter out and match them with this upstream tracker, which is a silicon pixel detector, a silicon strip detector, then you have these downstream tracks. So this was the principle for creating the downstream track. You extrapolate the sci-fi seeds to the center of the magnet and use the kink to the upstream tracker. You filter out the used seeds which have been already used by these long tracks, and that's how you can get the downstream track. So just going into the details of this particular algorithm. You have the stack model, standard X state. You have the X, Y, the slopes, and the QOP estimation. So we start with first estimating the magnet point, and based on this particular magnet point, you extrapolate these seeds to this center of the magnet point. You do the slope and momentum estimation, and then based on that, you calculate this tolerance window where you want to search your hits. Once you have defined this particular tolerance window, you look for the hits in this particular window, and then for each combination, you update the momentum, and then you see what exactly can be the best momentum estimation for this window. And then out of that, you do the chi-square fit, and then you select the best candidates. At the end, you run the fake and clone removal. That's in a very simple way how a downstream algorithm has been implemented.
TXTY, what are they?
The slope, initial slope estimation
or
for
the slope of the
of the seed. We have the initial slope estimation from the sci-fi seed, so that's the. And so the good thing comes here is because the way this algorithm is implemented. This is very computationally expensive, and we have managed to utilize the really the features of the hardware which a GPU provides. So you have about 128 sci-fi seeds per thread block. So we have divided this whole algorithms in 3 different kernels, which does exactly certain things in parallel. So for example, here for 128 sci-fi seeds in parallel, you filter out the used sci-fi seeds. For each input sci-fi seed, you extrapolate to the last layer of the UT station, and then you store up to the 10 best candidates, and then update the slope for each candidate using the magnet point and so on. Then you do in the second kernel at the parallel for 256 candidates at the same time. You add hits from the rest of the UT layers, find best combinations of the hits by adding the UV hits, and then you compute the scores based on the distance between the extrapolation versus the real position. And then in the next, you basically find the best candidate based on the scores and the chi-square fit. You check for the duplication, perform the ghost killing, and at the end you create the output in a SOA container. It's a structure of array container. So one of the key things which we managed to do is have this ghost killing neural network in the high level trigger for the first time. This is the first algorithm in the high level trigger configuration which uses this ghost killing neural network. It utilizes 8 variables as an input. It's a a single hidden layer 14 feed forward neural network. And we trained them basically with the min bias BS255 samples. And in order to boost the speed, in addition to that, we utilize certain C++ CUDA tricks, for example, using the statics tricks and some of the fast math functions which the CUDA and C++ provides, and basically rolling of the loop so that you don't execute one single condition of loop one by another, but you roll the loop in such a way all the conditions of a loop are executed at the same time. So for example, these are one of the and the algorithm performs very good. You have good physics efficiencies up to 80%, and you can see some of the efficiencies and good momentum resolution as well. And with this, we have about 82 kilohertz in rate at the HLT1, and which is still quite manageable, but with a full trigger configuration, which was not possible before. So now I just want to, this is the main part I want to showcase here, the efficiency of track reconstruction. Yeah, 75 to 80% of the tracks we are able to reconstruct correctly. We checked with different samples, and it is agnostic to different samples. So, I mean, these are, for example, different configuration of the algorithm. So, how is the differences in the performance? So, for example, here, if you run the forward and as well as the matching both, in addition to the rest of the HLT and downstream, this is the 82 kilohertz. If you run only downstream, UT decoding and the matching and don't run the forward, which is, then you can still save a lot of space in the trigger. So this basically means that in the order of 500 GPU cards, you are able to implement the entire HLT1. Even running the full configuration. Now, this is the major impact on many decay channels. We were interested in one particular decay channel, lambda B to lambda gamma, but now you can see here, it's not just that. In the standard model, for example, cascade B to cascade gamma, this has not been seen yet. There were searches and there are limits, but this has not been seen yet. And you can see for this particular channel, 25 times more downstream tracks are there as compared to the long track. So you are going to have 25 times more statistics which were not possible before. And like that, you have this omega B to gamma. This has also not been seen yet. And you have 13 times more statistics. With the same detector, same everything, huge impact on the statistics with different decay channels on the lambdas and K-shorts and so on. Impact on the charm physics as well, we'll be able to do much more, we'll have much more statistics for that. So this is the highlight for the standard model physics. But now looking at many of the BSM models which we looked into in the beginning, for example, you see here LHCb's capabilities of probing BSM physics can have significantly improved. So you can see here in this particular case, you have this dark boson model in the hidden sector where standard model Higgs mixes with the Higgs prime here. And the decay width here mainly depends on the coupling coefficients. And if you basically see the efficiencies, without downstream, LHCb could probe only up to 100 picoseconds with very low efficiencies here. And those also very bad when it has the low mass Higgs, if it was low masses. But with the downstream, now you are able to have this whole region with beyond 100 picoseconds up to 2000 picoseconds. So this was before we did the downstream, we did this studies. But then we have the downstream, and then we basically worked on checking other physics channels.
You have time.
Yeah.
The scales on this one.
So this is the if the Higgs prime mass is in the MeVs given, and you have, for example, 1 picosecond, 10 picosecond, 100 picosecond, 500, 1000, 2000 picosecond. So here you can see the efficiencies were good, like more than 50%. This is basically the efficiency. So if with the long tracks, only if you were using the long track, you would be able to study this, which is up to 100 picosecond. But if you include the downstream tracks, then you cover this region as well, which is beyond 100 to more than 100 to 2000 picoseconds. It's a lifetime of the decay, a lifetime of this Higgs prime, a possible Higgs prime.
Okay.
It's for how long this Higgs prime can be there before decaying into the decaying into the standard model particles, for example, in this case, 2 muons and kaon. So what exactly could be the lifetime of this particular Higgs prime? The possibility of
But normally you would expect a much smaller lifetime, right? Is this 1000 picosecond normal? I mean,
we don't know. It could be. We have not seen it, but it could be there in that particular range. We have already made searches in this, and we could not find. Yeah. Now, so this is the lifetime range here. This is the lifetime range. Higgs prime, it can be something, but so this was before we did it. But after we did the downstream, and a lot of theorists also got interested, and then we have recently published this particular paper where LHCb's potential to discover long-lived particles, new physics particles with lifetime over 100 picosecond. And I mean, if you remember a few days back, Professor Subir Sarkar had made a very nice lecture where he discussed the dedicated lifetime frontier experiment, like such as Phasor 2 and Phasor 2, which is coming, which is basically they're placing much farther to the interaction point so that you can basically probe certain areas. Now, if you compare the possibility which LHCb has with these reconstruction algorithms, so here you see this particular dark red is the Phasor first phase, and then the dotted red is the Phasor 2, which is a future detector which is going to come. With the LHCb downstream, we are able to cover almost all the area which Phasor 2 would cover. In some cases, it goes even beyond. I mean, here you can see some of these observables, it goes even beyond and then goes much farther than what a dedicated lifetime frontier experiment is doing. So, and not just one particular case, for example, you have this as a dark scalar model, this is a dark photon model. Here also you have another type of dark model. So this area, you are able to cover this area which dedicated lifetime frontier experiments like Phasor, Mathusala and so on much further. And similarly for...
No, I was saying, basically saying LHCb says that we don't need to have
Phasor 2, right?
We are not saying that. We need to have that because it's important to have the complementary measurements.
Can you go to that slide? Is there still some complementary region that Phasor 2, like LHCb? I mean, sorry, can you show me once again what is Phasor 2 versus the LHCb new thing?
So here, in this particular dark photon model, you have this dark red is the Phasor 1. This dotted red is the Phasor 2.
Right.
And the dotted blue is the LHCb.
So is there any kind of non-intersecting region between the two, or it is fully?
There are actually. So I mean, in this case, for example, in the dark photon model, Phasor 2 is slightly having higher, much broader area as compared. But for example, in this case, LHCb has much broader area. In this case, it is like this, for example, heavy neutral leptons. In this model, you see this. I mean, the LHCb is much more as compared to what Phasor can cover. Also, I mean, phasor is at a very high distance, so it would be very small cross section. So those are things also add up. So for example, this also in the heavy neutral lepton case, and this is the axion-like particle where you also have some complementary area, but not. So the point is, LHCb in the beginning has not been basically designed to do this kind of physics, and it was not. But now by investing in the software, so with this I come to my summary. So we have made the important contribution to the physics program, the major international high energy physics experiment in the development of the new high-level trigger system and the algorithms which are going to be running for LHCb Run 3. We have built a first full GPU-based trigger system where I've contributed in the last 5 years. And this places LHCb as a lifetime frontier experiment. For example, in Run 1 and Run 2, we could probe up to 100 picoseconds, but now we can even go further from 100 to 2000 picoseconds. And it's not just the standard model physics. Standard model physics, we are going to have much more statistics, going to be able to do much more. But also in the beyond standard model physics, I have shown you how our reach has increased. So this shows that huge physics gains are made possible by investing in the software and algorithms. It's an important experience gained for the large-scale data-intensive sciences in general, and this is an opportunity for TIFR also to be part of this major endeavor. With this, I think I've covered in my time limit. So thank you very much. I would be happy to take your questions.
Presentation of what work you have. Is there any questions? So please.
Yeah, thanks for the nice talk. I have a couple of doubts, clarifications. When you are recording, every hit on the detector, right? So then you are recording every hit, and then as you mentioned, then in software you are, forming the trigger. So your whatever, reconstruction algorithm. So just to know, once you record, and how long you store the data before you reject the data,
So yeah, for yeah.
How much time?
Yeah.
Yeah.
Yes.
Yeah. So for example, here you are at the high level trigger 1 level, you are taking basically reading the data at the line rate about 5 terabytes per second. And it's, I mean, there is basically not, as you can see, there's no storage. So you have to be able to process at that rate, just being in the cache memory of the machine where you are basically building the events. So it has to be basically in the real time.
Yeah.
It's within few milliseconds. Yeah, that's true. And it's in the ranges of few 100 milliseconds. That's correct.
And
but
then
less than a second. Yeah.
And then you are rejecting, which
then you
are
make a
not,
decision whether you keep it or reject it. Yeah.
let's say, your algorithm, always can improve, right? Let's say you find there is some problem in your algorithm, right? That now you have rejected your data.
Yeah.
So how that could be a risk,
so
right?
Then what you do is basically, as you can see, we take in between some runs where you basically record the data at full line rate. So this is what it comes to basically alignment calibration part. So in between you have these different runs where you basically store the data at full line rate without running any trigger. And you continuously check the performance. You continuously check how it is basically happening, what exactly is in your raw data versus what you have the decisions from the high level trigger, and whether it was asking it to reject or asking it to select. And if it was asking it to reject, if there was something which was interesting, which we were losing, and so on. So those kind of analysis we basically do during the run, as well as before in the simulations.
Yeah, from the very beginning, you should have a very good confidence on your algorithm, because,
True.
Once start, recording and, rejecting the data, you will not get back, right? Yeah.
That's true. I mean, this is why, I mean, it is super important that you don't reject the interesting data. And there also, I mean, we have different streams where in some of them you basically have this calibration, you have the full event rate where you basically store about 26%, you write them as it is as the raw bank and you pass on to the next stage. And then you have this turbo where we call it, basically you only store the reconstructed objects and not the full raw events.
Okay. And what format you are storing the data? Which format? Format.
So we have a custom LHCb format. We call it MDF in the sense we have a custom built LHCb format.
Is the data storage in root or something? Or
No, it's the root objects, they come much later. So first with the raw data format, it's basically a custom data build format, which has been designed in keeping in mind the different detector channels and how they are and how best you can store them. It's much more complex than root. Compress, yeah.
Okay. Yeah, thank you.
Between two trigger, if you have multiple same kind of particle, then how you distinguish between them? Say between two trigger, 5 proton created, so they will have same track. So can you distinguish 5 protons as 1, 2, 3, 4, 5? Or
I'm not sure if I get the question right. Sorry.
I mean, I give an example.
So there are like 25 nanoseconds. You have the.
So he's saying you have, let's say, multiple collision happening between proton. And let's say your beam emission is coming from one collision, one proton-proton collision.
Yeah.
And if you have beam emission coming from the other collision, can you distinguish the beam emission from this to this? That's what you were saying?
Yeah. So I mean, that's where the detector electronics comes into picture. So you would see the different detector channels as well as the readout electronics and so on. That has to be built in such a way that it is faster than an average collision rate. So like every 25 nanosecond you are colliding the beam, but your detector electronics should be much more faster than that. So to be able to differentiate between the two collisions.
And the other thing is, unlike if you have heard of any CMS talk, typically in LHCb, they take the data at what they call Lumi labeling. So on average, you have very close to 1 to 2 what you are thinking of, like multiple interaction happening at a time. This is very less in case of LHCb. Almost close to that. Almost close to that.
When the data is read out from, let's say, one particular portion of the detector, then you will be combining with the information from the other portion of the detector. But each information has timestamp with respect to the LHC collision clock. So that's why when you are in the multiplexer, etc., when you are combining, you have to first check the timestamp from there, so that there is no mistake of combining information from different collisions.
Is there any?
Yeah, so you have these different vectors, different links, and so on.
So this event with that takes care of.
Yeah.
I think Parag, there are also questions on the Zoom.
So,
Please.
I think Satya had a hands up. So maybe
You can first start with Professor Vivek Datar.
Vivek Dattarji, you have a
Okay. Yeah, I had a question. Perhaps I missed it, but is there a possibility of detecting 2 photons decays of long-lived particles in this experiment, especially towards the lower mass?
I think we have studied some models which involves 2 photons in quite lower mass regions. Just a moment. Let me, not this one. We have certainly have some models where you have 2 photons in the final state, and we have studied the effect of it, and and maybe it would be, yeah. Low energy, yeah, it would be very challenging, yeah.
So you have the electromagnetic calorimeters in this detector. So, maybe if you could go back to the slide that shows the detector setup, it might be a little clearer, perhaps.
Mainly, calo info we don't particularly use in the HLT1 level. Here, it's mainly all the decisions are with the track based, and you use the calorimeter info in the high level trigger 2, where there's you have much more time in comparison. But we, as a combined, we studied some decays. It is, I think, there in the paper which particular decays we studied for which involved 2 photons.
Okay.
Here's the detector. Yes.
Yeah. Okay. So you have the calorimetric detector.
Yeah.
Maybe so on the scale of what, let's say about 5 meter or 10 meter, you could measure the decay, is it?
Yeah, it's after 12 meter, between 12 to 15, as I can see here.
Yeah.
So
the decay has to occur before that, and then you have to detect the 2 electromagnetic showers, and then try to reconstruct whether they start from the same vertex.
Yeah.
I mean, within the experiment.
I mean, if you look at the configuration here, let me go to that slide.
No, okay, let me be specific. My question is, motivated by this X17, which has been, there is a claim from some low energy nuclear physics group in Hungary, who claim that there is a 17 MeV particle. Now, can LHCb with the new triggering system, put either find it or put stringent bounds to rule it out at the level that is being claimed?
What is the decay channel for that? 70 or 17?
So it does decay into E plus E minus.
Okay.
But it could also decay into 2 photons.
Okay.
And the E plus E minus channel has been studied.
Okay. So we do have electron ID in the HLT1, and we certainly study how it would be, but I'm not so sure. I mean, I would have to check that.
Okay. Thank you.
Thank you.
Satya, you have a question?
Yeah, I mean, it is a bit of a generic question, Brij. Very nice colloquium. You did mention in the summary that, talking about whether TIFR joins LHCb or this effort, you said. But on the other hand, CMS2 for the new upgrades, etc., has a similar both hardware and software getting prepared for triggering and track reconstructions online and so on. I'm sure they are also extensively using GPU-based hardware machines. So are you trying to contribute into those efforts in some way?
I would certainly be joining these efforts at some point, depending upon the work which is there as well as the interests. But for now, in the light of this particular work, it's quite interesting to see it through, because now we are going to have this data, which is going to be we are going to have in 2024. So it's as an experimentalist, it's something to be able to see the real data and see how your things are performing as compared to in the simulation. But yeah, certainly. I mean, so the thing is, this particular work is quite experimental agnostic. The experience which gained in writing these algorithms is basically you can apply anywhere. So and there are a lot of projects you would see. For example, there is a tracking project which is ACTS, which is experimental agnostic. So they are trying to build this universal tracker software framework, which any experiment can adopt. And so that level, for example, the contribution there can be replicated and can be useful for the CMS, for LHCb, for any other experiment. So I mean, kind of similar to how GANT is being used by all the other experiments. So these, I mean, the work as well as the skills learned and experience gained are quite universally be applied to any other experiment.
Okay, just a small question follow-up. You can say, so I'm now talking about the real hardware. You talked about of the order of 500 GPU boards. And so do you kind of use them off the shelf hardware, or do you sort of co-work with an industry to produce something more of custom built hardware in this sense? How do you get this hardware in place?
So when you say hardware, you mean the hardware of the level trigger?
The GPU board, you mentioned about the hardware comprises of about 500 GPU boards, right? Somewhere you mentioned.
I mean, for example, I can show you in this using this. There are even some backup slides where I might be able to show it better. But in any case, so here, for example, you have this particular machine where I've shown here 2 GPUs. So it's a standard off-the-shelf 4U machine which can take up to 8 PCIe boards. And there, what we have is we have the TEL 40s, which are our FPGAs for basically data taking. Then you have GPUs for doing the reconstruction, which are also PCIe based GPUs. And then you also have the network cards. So they are quite commercial boards.
Commercial. Okay, that's my question. Okay, thanks. Yeah.
I have a very quick question. Can you go to the next slide? You mentioned somewhere that you have a detection efficiency roughly 75 to 80% with a trigger 3 mechanism, run 3 mechanism compared to the run 2 mechanism.
Yeah.
Is that the number you derived using your calibration in that what you showed in a 6% calibration event you have mentioned?
I mean,
how do you work out this number between run 2 and run 3? Is that the way you did?
These numbers are basically only at the bandwidth divisioning point of view. So when we are, for example, in which mode we want to run it. For example, this calibration event 6%, we take it directly even without reconstruction so that you can later on check and so on.
So based on those 26% of the time which you have acquired data,
yeah,
you find out the selection algorithm what you run and how you.
And then based on these numbers, you can basically calculate how efficiently your trigger has been working and so on. So this is just, I mean, to represent how the bandwidth can be divided.
So basically error in your algorithms and things are based on those 23% of the data which you have taken without any trigger mechanism.
All this work which I have presented, this is based on the simulation samples.
Oh, simulation samples.
Simulation
not
samples.
The real data.
We are going to have the real data now.
Okay.
Starting with the run.
So maybe you can do a second asset colleague once you have the data.
And that's where, I mean, collaboration is very encouraging us to take up these responsibilities of checking how these algorithms and the trigger performs in the with the real data.
Yeah. So, any other questions? Yeah.
Measured by knowing the truth from the Monte Carlo. So simulation, and then you pass through the whole chain and then see how much you learn.
Makes sense.
And then, as he says, that with real data you compare and then you see why you have to keep things.
Thanks. Makes sense. Is there any other questions either online or things? Well, I invite everybody to appreciate the very useful and very illuminating asset is given. Is a very good quality and really impressed in work.
Thank you.
So thank you very much.
Thank you very much. Thank you very much.
Take this opportunity to present you with the memento of 40 years of asset performance. Yeah.
Okay.
Thank you very much.
Wow. Thank you very much. Thank you.
I invite everybody to join for the team.
Thank you. Thank you. Thank you.
Nice talk, Brij.